Welcome back, fellow scientists. So today we're going to clean up Unit 7, which is evolution. So on OneNote in the content library, blank notes. I tried to give you some blank notes, but apparently I failed with this one. So this is the first subject that we're going to be going over, evidence for an old Earth. And then the next video, we're going to do cleaning up evolution, and that one I did succeed in providing you with blank notes. I am going to be taking notes over here under the content library in the class notes section. So even on this one that has some writing already, I'm going to be adding my own writing. And then of course, with the next one, then cleaning up, I saved the writing as I did with the last presentation. I saved writing from last year just because it'll be quicker for me to go through. So I will add some stuff, but basically, yeah, that's there if you want to use that. So evidence for an old Earth. College Board, I have my content standards right here. So College Board wants you to know that Earth formed approximately 4.6 billion years ago. Earth formed. And my understanding is basically that's like the oldest rock that we can find on Earth. So Earth had to be here for that rock to be here, and that rock dates back to 4.6 billion years ago. We'll get into how we actually do that later on. But 4.6 billion years ago. And then according to chemical analysis of rocks, Earth was too hostile for life to form until about 3.9 billion years ago. So BYA, Earth is too hostile. Earth is too hostile for life, right? And then we have our earliest fossil evidence of life, 3.5 billion years ago. Earliest fossil evidence of life, right? So we're doing that. That's what the College Board wants you to know, at least for that part, right? And so this is a diagram from your book. I believe this is chapter 18, possibly due to time constraints. We won't have a reading interview guide on chapter 18, but I encourage you to kind of look through it. Last year, because we had a little bit more time, what I had people do is I assigned individuals different epochs or different eras, right? So here's Darius, right? Here's Sydney, here's Grant, Abby, Allison, right? Whatever. So those are all the people that took the class last year. And I had them make a timeline square. You guys may have seen that hanging up above the door into Mrs. Lindsay's room. But each of them made a timeline square, and I asked them to show me what the landforms look like. I asked them to show me kind of like representative plants and animals, flora and fauna from that time period. And so then we would put them all together in a big long timeline, and then we talk about that. And basically, that whole assignment was to get people to see that life started out simple, right? As we dig down in the fossil record, and this will be a theme, simple to complex, right? And then the landforms are changing. So land changes, atmosphere changes, sea level changes, right? So all those things. So I know that you guys are smart and you guys can kind of get that and you can understand that. All right, so here we go. Chapter 18, question number 1, how old is the Earth? Answer number 1, if you read the Bible as literally as possible and you have all those years and you have all the genealogies and everything like that, you can guesstimate that the Earth is about 6,000 to 10,000 years old, right? So that's answer number 1, which I personally believe, but I have no scientific evidence to back that up. I only have biblical evidence to back that up, right? Answer number 2, the Earth is 4.5, 4.6 billion years old, and there are vast amounts of scientific evidence to actually back that up. We talked in regular biology, right, about relative dating, right? So the newer species are closer to the surface, and then the older species are kind of lower to the surface. So that doesn't give us necessarily numbers, but that gives us kind of a progression, right? And here we see simple, right? And then as we get closer towards the surface, it's more complex, right? And then if we want to put actual numbers to it, we have our radioisotope dating. And again, we talked about this in regular biology, but carbon-14 is a classic isotope. Remember, an isotope is an atom that has gained or lost a neutron. So it has the same number of electrons. It doesn't affect its chemical properties. It has the same number of protons. So it's actually carbon. It's not something else. So carbon-14 has too many neutrons in its nucleus, and so it's too heavy, so it goes through radioactive decay, and we can measure that decay, right? And then as carbon-14 decays, then it turns into nitrogen-14, which is obviously a different element. And so we can dig up fossils and we can analyze the amount of carbon-14 and we can analyze the amount of nitrogen-14, and we can assume that, based on like the chemistry and geology of the rocks and kind of how much carbon-14 we have present now, how much carbon-14 was present back then, and then we can cross-check that with the amount of nitrogen-14 that has accumulated. And we know the half-life, how long it takes for half of a sample to decay, and everything like that. So in our culture, at least in the Christian culture, radioisotope dating, radioactive dating takes a lot of knocks, takes a lot of hits, but if you really dig into the science, like it's actually pretty convincing, and it's actually pretty solid, right? So carbon-14 has a fairly short half-life, 5,700 years. So we could use it to date things from 100 to 60,000 years, right? Potassium has a half-life of 1.3 billion years. So we can use it to date things anywhere from 10 million to 4.5 billion. And like I said, in the Christian community, radioisotope dating takes some hits because if you're dealing with billions and billions of years as your time frame, if you're off by a couple thousand years or tens of thousands or hundreds of thousands of years, like that's not really a big deal in the grand scheme of things. If you think that the Earth is 4.6 billion years old, but if you think that the Earth is 6,000 years old and you get a sample and it's off by 10,000 years, well, then all of a sudden that's a big deal, right? So it all depends on your frame of reference. It all depends on your point of view. Suffice it to say, radioisotope dating is scientifically valid, and that's where we get a lot of our evidence from the age of the Earth, or for the age of the Earth, rather. Here's another one of our themes, right? As we go from older fossils to newer fossils, or as we dig down deeper, right? We're basically going back in time, right? And we see this trend of simple, right, down here all the way up to complex, right, up here. And then, of course, we had our dinosaurs, and your book talks about the dragonfly with a 2-foot wingspan or whatnot. We've talked about this in class. More oxygen leads to larger body size, and we have geological chemical evidence for that, right? And then we have, of course, our layers, by the Grand Canyon. This will come up later. And here we have our time frame and different types of animals, and when there were a lot of them, and when there were not a lot of them, and all sorts of stuff like that. So another area that we get evidence for old Earth is plate tectonics, right? So you guys have heard about this before, seventh grade, eighth grade, hopefully science class. The Earth is riding around on continents are riding around on giant plates that are riding around on the molten core of the Earth, and there are some weak spots in these plates, like this mid-Atlantic ridge right here where magma is constantly like kind of spewing up from the ocean floor and making new crust, right? And so then that pushes South America this way and that pushes Africa this way, right? And if you've seen Al Gore's movie An Inconvenient Truth, then well, these kind of look like puzzle pieces, like they fit together, and they actually kind of do look like puzzle pieces that fit together, not just their shape, but scientists have analyzed the rocks and different things like that, and there's rocks here on the east coast of South America and on the west coast of Africa that have the same geologic signature made at the same time. There's fossils of animals that couldn't swim between these continents. They're on South America and they're on Africa, right? So that leads to this view. Oh, and then there's the Appalachian Mountains right here, and then there's the Caledonia Mountains right here that seem to be kind of the same mountain chain formed at the same time, same chemical structure, same geologic structure, right? And so then that leads us to, oh, well, the Earth used to be connected and all the continents used to be connected in Pangea, right? And different things like that, right? And we can look at, right, currently like the Red Sea, right? And what is that? I forget. Anyways, that's a current example of plate tectonics. The Great Rift Valley, that's what it is. And so pretty soon, you know, in like tens of thousands or millions of years, then the Horn of Africa is gonna just say peace. We'll see you later, and it's gonna go out here, right? And then there will be another island off the east coast of Africa, right? And volcanoes, right? The Earth is volcanically active. So we see lots of evidence of that, right? More evidence of old Earth. There have been large meteors that have impacted Earth, you know, at certain times. And meteors are actually rich in a chemical called, I gotta look this up to make sure. Dun, 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 Iridium. There it is. Iridium. Iridium. And so meteorite, right, hits and then vaporizes and then throws up this big, huge cloud of dust. The big, huge cloud of dust like goes around the whole entire world, and eventually, like all dust does, it settles. And so then, as we dig down, or as the process of erosion reveals these layers to us, then we have this thing right here called the KT boundary, which is iridium rich, which suggests that, okay, so just before this time there was a violent meteorite impact, and then that sent a big cloud of dust, and so then we see extinction of all of these animals that lived in here, and then we see adaptive radiation or new species above that boundary. So that's evidence for the old Earth, and we'll talk about adaptive radiation and stuff like that in the next video. Another place that we can go is strolomites, right? So strolomites are basically just layers and layers and layers and layers and layers of bacteria, right? And so these are living current day strolomites right now. I think this is off of Australia, possibly. But strolomites, because they're kind of fossilized or preserved, or like, what's that called? The wood that turns into stone. You guys are saying it right now, and the only problem is I can't hear you. um, Anyways, it'll come to me. But these are preserved strolomites of bacteria, and so yeah, so that's another place where we get maybe like the chemical conditions of Earth, or maybe just the age of the Earth, because it takes a certain amount of time to make a layer of bacteria, and then you count through the layers and you say, oh well, I wonder what happened here. I wonder what happened here. Let's look at the chemical composition. Petrified. That's what it is. Petrified wood. So these have been petrified, and then yeah, turned into fossilized, turned into rocks. So all right. So that kind of concludes like everything that the College Board is going to ask you about. But then it's really interesting to me, because even when I was like going through like post undergrad education, like fossils, you know, something has to die and then it has to get buried, and then, you know, quickly, and then it has to be well preserved. And fossilization is this process that takes lots and lots of time. But then Dr. Mary Schweitzer, who I'm going to talk about here in a second, I heard a lecture from her, and she's like, actually, like we don't exactly know how fossilization happens. And so here's a couple things that, you know, science is still kind of trying to work out and trying to figure out how this fits in. So here we have a fossil of a fish eating another fish, right, which indicates kind of like rapid, catastrophic, you know, event that froze this in time. Here we have a fish giving birth, right, which again illustrates kind of like catastrophic, rapid burial. Here we have an animal right here called a coelacanth, which hasn't been in the fossil record. Let me get my dates right. Oh, come on, where is it? Yeah, I don't have it on here. Anyways, we have a coelacanth, which I believe hadn't been in the fossil record for maybe up to 10,000 years. It could have been longer than that, but we thought that they were extinct. And then lo and behold, like in the 80s, I believe it was, a fisherman off the coast of Africa, I believe, pulls up something that looks very remarkably similar to this fossil right here. So we hadn't seen any fossil records of them, and we thought they were extinct. But then lo and behold, here they are looking very similar to the fossil. So it's like, oh well, maybe the fossil record isn't, you know, like entirely complete. So that's that. And then I also want to direct your attention to a video. If you were in class, I would show this video, but I just searched Mary Schweitzer B-Rex. Like I said, I had the opportunity to hear her speak live and in person. And so 60 Minutes did a special on her, and basically, check this out. She was working with Grant Horner, and he's like the most famous paleontologist. Jurassic Park. Alan Grant was based off of his character, and or him like his character was based off of him as a real person. So famous paleontologist. He found dinosaur bones, and he has so many of them, he doesn't mind breaking them. So he lets Mary Schweitzer break them and dissolve them in acid. And then here's what she finds. So they find soft tissue from dinosaur fossils and it's amazing, and they try to get DNA, but they're not. And then there's all sorts of controversy because if this dinosaur is actually millions and millions of years old, this soft tissue shouldn't have survived. But anyways, that's so if you have time, go on and watch that. That's amazing. Um, and then, of course, this is just, where's my mouse? This is just a repeat of what we've done in regular biology, right? So there are some geologic events that happen very rapidly. So we use Mount St. Helens as an example, which coincidentally came up in our teacher meeting earlier this week as another time of like social upheaval, and like people were panic buying, at the stores, and people were stranded in cities where they didn't live because they shut down the interstates and everything like that. So May 18th, 1980. I was approximately a month or two old, something like that. So I have lived through Mount St. Helens. I don't remember it, but I was present on the earth at this time. So that's what Mount St. Helens looked like before, right? And then this big old bulge on the side starts growing at a rate up to 5 feet per day, right? And normal mountains don't grow that fast, just FYI. Then all of a sudden, the pressure inside the bulge is too great, and the pressure bursts through the surface, and then it's just like, yeah, volcanic eruption. Lots of lahars, mud flows, ash, debris, rocks, different things like that, right? Big eruption, and it fills in like valleys that used to not be filled in, right? And then here we have this lahar, this volcanic mud flow of ash and different things like that. And that just happens to block these rivers and lakes and streams that used to have a nice little path, down there, but they don't anymore. Well, the water, like, it doesn't have any place to go, so it builds up, builds up, builds up, and then finally it cuts through all of this like newly laid down debris, and a big surge kind of goes through, right? And then, and then it slows down, then it dies down to a trickle. And so we have here, just to give you a scale, right? We have humans here, and that's kind of they're surveying it and they're taking data and doing all sorts of good stuff, right? So that picture, of course, reminded me of this picture, right? And so, can geologic changes happen very quickly? Yes. Do they happen very quickly, very often? No, but is it possible? Yeah. So for the Grand Canyon to form, we would just need a volcanic source close to the Grand Canyon or big enough. And so, of course, Yellowstone National Park, Old Faithful, right? It's still kind of volcanically active. There used to be a super volcano where Yellowstone is right now, and here is the ash bed that Mount St. Helens laid down. And then here are successive ash beds that we've found in the United States from when this super volcano erupted many times over the course of the Earth's history. So, can we have very rapid changes? Yes, but we can also kind of realize that there's a lot of scientific evidence that with those rapid changes, the Earth is also very old. So, thus concludes our evidence for our old Earth. Our next video is going to be cleaning up the theory of evolution, cleaning up Unit 7. And so I hope this has been helpful. This has been Mr. Leo, and I will see you on the flip side.